Today we are going to finish the discussion about time value of money. We will discuss with you some additional models how you can compute present value and future value of some special forms of cash flow, which are quite useful in special cases. And then we will move, next week we will move to the practical applications of all these calculations, how to use these models to evaluate stocks, bonds, and some other securities, how to apply all those models in the real financial activities of the company. But of course, before we do this, we need to finish our discussion of the theoretical and mathematical framework. So what do we have at the moment? We have covered the basic operations of future value and present value calculation. Single period case, future value, present value for one payment, multi-period case for one payment, and future and present value for the stream of payments for the stream of cash flow. Please remember that once you are given different investment opportunities, different options, how you can receive your money, you must compare these opportunities according to the rule of time value of money. And this rule says that you must compare money at the similar moments of time. You cannot compare amount today and amount 3 years after. It's not possible. You must either convert today amount into the future, or you need to discount the future amount to the present time, and then you are able to compare these two amounts. That's the main purpose why we are doing all these mathematics. If you want to know what is the expected result in monetary terms of your current investment, usually this is about bank deposits, so compute future value. If you want to know what is the maximum price that you are able or you are ready to pay for some future stream of payments, profits, whatever, compute present value. So these are the main important things that you need to remember from the past lecture. And formulas, of course, but formulas are not necessary to remember. You just need to know how to use those formulas. That's the main issue. That's the main expectation from my side. Now, there is a special form of a cash flow called annuity. So what is annuity? An annuity is a series of equal payments made at fixed intervals for a specified number of periods. So we must have all these conditions together. There must be equal payments, so they are the same, like 10, 10, 10, 10, 10, for example. Fixed intervals, which means that intervals between them are same, like 10 today, 10 after 1 year, 10 after 2 years, 10 after 3 years, and so on. So every time the distance between two elements is the same. For a specified number of periods, we must know the exact maturity of this cash flow. It's either 3 years, 5 years, 10 years, 30 years, doesn't matter. What matters is that it is finite. We know when this stream of payments ends. For example, where in practice we can find such cash flows? Equal payment house mortgage. This is the most popular example of annuities. When you take a loan to purchase a house, usually you pay monthly equal amounts with fixed intervals between these payments, and you know exactly when you will finish doing this, after 10 years, 20 years, 30 years, depends. interest payments on bonds. That's where we are going to apply this tool when we start our discussion of bond valuation. We will apply annuities there. Life insurance premiums. This is the opposite thing. When you pay fixed equal amounts to an insurance company, usually they call this product annuity, and then you kind of accumulate some amount of money, and once you have some issues with your health, or maybe you are dead, then the amount is paid to your kids or your spouse or your family, or if just some issues with your health, it's paid to you. Formally, for an annuity holds the following equation or equality. So we have C1 equals C2 equals etc. Cn. So all payments at every moment are equal, and we will denote it with A, just to make it simple. So we know from the previous lecture what is the general formula for the future value calculation when we start at time 0 and when we finish at the moment n minus 1. So this is the formula. Now, from the previous slide, we agreed that all payments are equal. So CT are equal, right? So if we use this equality, we can rewrite the formula for the future value of annuity in the following way. So look, I just plug instead of CT this term. Now we have a sum here, and inside this sum we have a common term, A. What can we do? We can factor this A out of the summation sign, like this. Inside the summation we have 1 plus r to the power of n minus t. What is this? Look, every time, every element of this sum, every term of this sum differs by 1 plus r. So basically we start with 1 plus r to the power of n plus 1 plus r to the power of n minus 1 plus 1 plus r to the power of n minus 2, and then we finish at 1 plus r to the power of 1. We have, so just to make it slightly useful, we factor out also one of these terms, 1 plus r, out of the summation sign. So we just change the index here. Nothing happens here. We just change the index. Instead of 0 and n minus 1, we take 1 and n. So this is just to make everything formally correct. So now, this sum is a sum of geometric series. I hope you remember something like this from your school mathematics. And this is convergent geometric series. So convergent means that it goes down. And once this sum, this is a finite sum, basically doesn't matter whether it converges or diverges. Nothing is wrong with that. We are able to find this sum with a single expression. In the school, we must be able to do that. If you're not sure how to do that, use some search engine in order to find it. Basically, we have the following formula for this case. The whole sum, it doesn't matter how many terms do we have inside, the whole sum can be evaluated with the help of this expression, 1 plus r to the power of n minus 1 divided by r. That's all. Now we use this expression here instead of this summation sign. And finally, we have the following expression to evaluate the future value of annuity. This. Well, in principle, we can multiply by 1 plus r here, and then we will get something less nice than we have. So the feature that annuity has equal payments gives us an opportunity to compute future value in a simple way. It's much simpler to evaluate future value of annuity, consists of 10, maybe 200 payments, than to evaluate future value separately for every single element, like we did in the previous lecture. Some important details about annuities and about future value of annuity in particular. Be careful, really careful about timing. What does this mean? So here, on the previous slide, timing is represented with these indices. T equals 0 to n minus 1. So with the limits of summation, where we start, where we finish. And look, we derived this formula for an annuity that starts at t0 and finishes at tn minus 1. This is an important thing. So if annuity starts at t0 and ends at tn minus 1, and we call this form of annuity annuity due, because it starts in the beginning of every period. Then the formula is this. So the formula that we derived. But let's look back. This expression differs with this expression by a single thing. The limits of summation are from 1 to n. So we shifted all payments one period forward. Therefore, if you have an annuity where first payment starts at t1 and last payment ends at tn, and we call this deferred annuity, then future value is computed without this extra term 1 plus r. You simply multiply a by this term. That's it. I don't give you derivations of these formulas. I don't give you anything. You just need to understand when to use both formulas, when they are applicable. And now we will look at the examples, and I hope you will understand how this looks like. So, a very generic example, if you deposit 100,000 rubles at the end of each year, this phrase is important, at the end of each year, for 3 years, in a savings account that pays 5% interest per year. How much will you have at the end of these 3 years? So who can answer which case of these two we have in this example? Is this the first case or the second case? When you deposit money at the end of every period. Any ideas? Which of these two cases you have in the task when you put money on the savings account at the end of each year? Is this annuity starting at 0 or is this annuity starting at 1? Guys, don't be silent. Suggest something. I'm not punishing you for wrong answers. I'm not giving you minuses for wrong answers. Just try to suggest something. Try to turn your brains and answer something, please.
We should start at 1.
We should start at 1. Why?
I'm not sure, just I see the
So
third year.
why you think that we start at 1? Because 0 is now, and we want to put money at the end of the period. 0 is always now. If we put money at the end of the period, we need to wait until this period finishes and we deposit our money at the moment T1, not T0, because T0 is now. And the question explicitly says at the end of each year. It's not the beginning of a year. Okay. So this is a deferred annuity starting at T1. And we know that for the deferred annuity, we must use this second formula. So just need to plug everything inside and compute what's gonna be the future value of this annuity. So this is 100,000 multiplied by this expression 1 plus 5% to the power of 3 minus 1 divided by 5%. The result is 315,250 rubles. Right? So this is in 1,000 rubles. This is your result. So in principle, you might have calculated the same result using the same approach as we had on the previous lecture. You take separately. Look, we are not doing it here. We are doing it here from the first moment. So here we compute separately future value of the first payment, future value of the second payment, and then future value of the third payment, which is the same as the payment itself. And together we have 315. So compare which approach is simpler, either to compute these things 3 times or to compute this in one single line. I guess this approach is much simpler and it gives you a chance to compute future value of 20 payments or 30 payments or even 100 payments much faster than this one. Now, the question is, what happens if all of these payments are made at the beginning of each year? So as you can guess, now we are trying to do to apply the first case when it's annuity due. So this is an annuity due, and future value computation differs only with one element. This element is here, because now every single payment gives you an interest for an additional period of time. So you made all these payments one period ahead, like this. So we start here. The first payment now is located at 0. It gives you profits for one additional period. So then the second is located here and the third is located here. So all these payments compared to the previous case are multiplied by 1.05. That's all. Questions regarding the future value of annuity. how to recognize whether it is annuity due or whether this is deferred annuity. Is this too difficult? So whether your stream starts now or whether your stream starts one period afterwards. So anything we should discuss at this moment? Okay. So for an annuity, we also can compute present values. We know that in a usual case, present value is connected to the future value with this expression. So now we know how to compute future value of annuity, right? So nothing differs in this case. If we know future value of annuity, we must be able to compute present value of annuity in the following way. So now we just plug the expression for the future value of annuity here. Then we make some simplifications. Look, I'm not canceling these two terms. Why? To preserve the same logic as we had for the future value. Now we have some expression here, so we can simplify this expression, but I prefer this form. And here we have this A, the payment of annuity multiplied by 1 plus R, just to discriminate between annuity due and deferred annuity in the same way. So if annuity starts at T0 and ends at Tn minus 1, then this is the formula for the present value of this annuity. If annuity starts, after one period, we just drop this extra term and we have this expression. Again, I am not canceling these terms just because of the necessity to preserve the same logic, the same construction here. Don't cancel it. So exactly the same logic as for the future value. So now let's try to understand several applications of a present value of annuity. So suppose you are offered the following alternatives. 3-year annuity with payments of 100,000 rubles. So you will receive 3 years 100,000 rubles. Or lump sum payment today. So lump sum means that you have it as one single payment. You need to compare. So basically the question is the following. So you don't need money during the next 3 years, so you are not going to spend them. So if you accept the annuity, you would deposit the payments in a bank account that pays 5% interest per year. Similarly, the lump sum payment would be deposited into a bank account. So you have an opportunity to deposit your money and you don't have a need to spend this money immediately. Which this phrase suggests that we have to apply time value of money rule. So the question is, how large must be the lump sum payment today? How large must the lump sum payment today be to make it equivalent to the annuity? So the question says lump sum payment today. If we are talking about today, it suggests that we need to compute present value. If it says equivalent to annuity, we have to calculate present value of annuity. So this is a deferred annuity. And we know that the present value of a deferred annuity can be evaluated in the following way. So this is 272.32. So the result of this computation, so this is just arithmetics, right? So I'm not discussing how to calculate this. I'm just showing you how to apply the formulas we have discussed. So the payment goes here, interest rate goes here, and then we have 3 years here and here. What is the meaning? The lump sum must be at least 232,320 rubles in order to make you indifferent between these two options, or between these two opportunities. So for you, if you have an opportunity to invest at 5% per year, for you it is the same whether to invest or whether to accept this amount or whether to receive 3 times 100,000 rubles. These two alternatives are equivalent to you, or you are indifferent between them. So look carefully that we are not comparing 300 in total with these. It is not correct. We are comparing a stream of cash flows annuity with 3 payments of 100 with this amount. This is the proper way how you compare. You just compute the present value of this. If you are offered 280, you accept 280 because this is better than 3 payments of 100. If you are offered 250, you will reject this offer because 3 payments of 100 are better. They have higher present value. That's basically the logic of making financial and investment decisions with the application of financial mathematics. Questions here? Is this clear? What are we doing and why we are doing this? So silence says me nothing. I still don't know whether you follow me or whether you are completely lost. So this is the worst feedback possible. Don't be silent, guys. If no questions, then no questions and we go further. Guys, respond me something. Give me some feedback, please.
Yes, Professor, please continue.
Thank you. So another example, very popular example of annuity application. So the question is, what would be your monthly payment if you took out a 30-year mortgage loan for 5 million rubles at an interest rate of 10% per annum? And there is a hint. A 30-year mortgage with monthly payments is 360 payments annuity. So if everything was clear on the previous slide, I will give you 5 minutes to compute the result here. So in order to calculate the answer, you have to first identify that this is a deferred annuity. You start your payments 1 month after you receive this loan. It's not right now. Your stream of payments to the bank starts in the end of the first month. Now, what do we know? Oh my god, there is a type. So after that, we just plug everything in the formula of a present value of annuity. So there is a payment which we don't know. This is our unknown monthly payment. We plug all parameters of this loan, interest rate. So since this is monthly payment, we need to divide annual percent by 12 to the power of 360. We have 360 months in 30 years. Here the same. And finally, we know that the result must be 5 million because this is the initial amount of your loan. That's all. You just compute this term and then you simply express A by 5 million divided by what do you have here. So the result is this. The monthly payment is gonna be 43 or almost 44,000 rubles. This is the result. Very simple. You know formula, you plug everything there, what is known, what is not known, and express what you want to compute. The next special case of a cash flow is a perpetuity. What is perpetuity? This is infinite annuity. So the annuity with no fixed maturity rate. Basically, you don't know when your stream of equal payments finishes. That's why you treat it as infinite. So a future value of perpetuity. If you take this expression, and when r goes to infinity, the whole expression goes to infinity. I don't prove it here. If you want, if you remember something from calculus, you must be able to do that. So basically you can apply something like L'Hopital rule, take derivative of the numerator, take derivative of denominator, and find that it goes to infinity. Because the derivative of denominator is going to be 1, and derivative of numerator is going to be m times 1 plus r to the power of n minus 1, so which gives you infinity. But the present value of annuity exists. So let's forget about this 1 plus r for a moment. And once we apply the ordinary or deferred annuity formula here, when r goes to infinity, the whole expression goes to a over r. Again, you can, in principle, you can apply L'Hopital rule here, take derivative of numerator denominator, and then you will be left with this, because numerator and denominator will cancel each other, and r is going to be left, I suppose. Don't remember, but again, I don't derive it here. So that's the final result. This is very simple and very useful in many cases. When you don't know when your annuity finishes, you can apply this formula to somehow simplify your calculations. Well, there is a practical example. Maybe it's from history, but still, well, where you can find such case. In 1815, after Napoleonic Wars, the British government sold a huge bond issue and used the proceeds to pay off many smaller issues that had been floated in prior years to pay for the wars. So basically, it was kind of consolidating a lot of small issues into one large issue of bonds, kind of restructuring of your loans. Well, the purpose of these bonds was to consolidate past debts. The bonds were called consols. That's why this name comes, and these consols, well, they exist even now. So suppose each console promised to pay £100 per year in perpetuity, because you don't know when this obligation finishes. So what's gonna be the price of each bond if the discount rate is 5%? 100 is your annuity, is your payment, in annuity, 5% is the interest rate. Formula for the present value of annuity is this, A over R. So let me know what is the answer. This is as simple as possible. $2,000. 100 divided by 5%. Very difficult. £2,000. This is your maximum price that you are ready to pay for this console if you have an opportunity to invest at 5%. Questions about perpetuities? Is that difficult? So let's continue. There are two additional cases when payments of annuities change according to some rule. And this rule is a constant growth rate. So we introduce a new term, a growing annuity. A growing annuity is an annuity with the constant growth rate. We call it G of cash flows. So every single period, your cash payments increase by the same growth rate. You have a geometric series of payments. So usually future value of this growing annuity is derived with the help of a present value of a growing annuity. So therefore, we need to know what is the present value of a growing annuity. So we have a finite number of elements. Therefore, future value must be also finite and present value must be also finite. What is the formula to calculate it? So the present value of a growing annuity is given by this formula. And what is the most important here is that R must be greater than G, because look at the denominator, R minus G might give you a negative number, and that's not what you want. So this expression is the present value of a growing annuity. C1, according to our previous notation used in the lecture number 2, we know that C1 is the payment at the first moment of time. So meaning that at the end of the first period. So we are talking only about growing annuity, deferred growing annuity. So the annuity that starts in the next moment, in the end of the first period. C1, G is the growth rate, and R is the interest rate. And here we have this expression. So let's see an example how we can apply this knowledge and this previous formula. So suppose a 65 years old person is contemplating retirement. So he or she wants to retire and expects to live for another 20 years. Has $1 million of investment funds, so like some free amount that can be invested somewhere. And this person expects to earn 10% on the investments and expects inflation on average of 5% per year. So what does this mean, inflation? So prices are gonna grow with this rate, and of course this person wants to earn kind of to withdraw every year 5% more. That's an idea, right? So if there is an inflation, of course, logically you want every year to receive more than than you had before. And this person wants to withdraw a constant real amount per year. So what does this mean real? It means that every year your payments must be indexed by the inflation. Every year your payments must be more by 5% than in the previous year. Well, the question is, what is the maximum amount, real amount in constant prices that he or she can withdraw at the end of each year? So we need to compute the size of the first payment. Basically, this size of the first payment is going to be the reference representing this real amount of payments that are going to follow afterwards. So inflation assumes that every year the person must receive 5% higher payment, constant growth. And we know that if you invest 1 million right now, this is gonna be a present value of a growing annuity with 20 years maturity, with 10% interest rate, with 5% growth rate. So we plug everything inside the previous formula. So that must be 20, not like this. So the power of 20 here. And then we express C1 from here. And so from here, C1 is gonna be 78,630, which is gonna be the size of your payment in constant prices. Again, you take formula, you plug everything you have, and you express the unknown variable from it. And the last special case of cash flows is called growing perpetuity, as you might guess. Annuity, perpetuity, growing annuity, and now there is a growing perpetuity. Well, growing perpetuity is a perpetuity with a constant growth rate of cash flows. Well, future value of growing perpetuity is of course infinity because it grows indefinitely, and of course you are not able to compute this future value. Present value of a growing perpetuity is very simple, this term. If you compare this with the previous formula here, you might find that growing perpetuity is, so the present value of a growing perpetuity is just this part. So this part, when n goes to infinity, this part goes to 0. And this is why condition r is greater than g is necessary, because when r is greater than g, here you always have a number less than 1. When this number less than 1 is raised to the power of n and then goes to infinity, the whole term shrinks to 1. To 0, sorry, to 0. And the whole term which shrinks to 0, 1 minus 0 is 0, 1 minus 0 is 1, sorry, and this term is left. That's how you can simply derive from the previous knowledge the expression for the present value of a growing perpetuity. It's here. And the usual, let's say, practical application of this growing perpetuity is the following. So you're offered to purchase a stable business with reported free cash flows of 1 million rubles next year. So next year, you can receive a cash flow of 1 million rubles. So because the business is stable, the profits are likely to grow at the inflation rate of, for example, 10% per annum. So every year you will be receiving 2% more, like 1,020,000, 1,040,400 rubles, and so on. So you keep doing this, and you don't know when this business stops. So this growth, this stream of payments lasts indefinitely. So the firm faces a cost of capital 8%, which means that this is your discount rate. And the question is, what is the maximum price you're ready to pay for this business? Maximum price, which means that you need to calculate the present value. First of all, a business brings the growing perpetuity. And second, we apply the formula given on the previous slide. 1 million as the first payment, divided by 8% minus 2%, and in total you have 16,666,667 rubles. So this is your maximum possible price that you are ready to pay for this business. Questions about growing annuity, about growing perpetuity, how to recognize, where to apply both? So here is the conclusion, let's say, of the lecture. We see all four cases together with the graphical representation, with formulas, and how do they look like? So on the top left picture, we have a simple perpetuity. You see that the cash flows are equal every period and they last forever. So the present values converge, it goes to zero. So therefore the present value of this is finite and it is able to calculate it, present CF over R or just A over R, depends on. So I borrowed this from another book using different notation. If it's a growing perpetuity, you see that it goes up, but still present values converge because R is greater than G. And this is the formula for present value of this growing perpetuity. So simple annuity with 7 elements. You see that you have only 7 elements, no more. Nothing lasts after 7 periods. And here is the formula. So you see that the formula looks different compared to what we have done. But if you open the brackets and if you rearrange terms, you will get exactly the same result. I can guarantee. So if you rearrange, if you basically subtract from 1 this expression, you will get the same formula. So there is no difference between this and what we have seen there. And but look, yes, there is also another issue with this formula. It is very similar to the growing annuity formula, but on the numerator here we have 1 plus G. So sometimes some authors prefer this formula. I prefer that one. So growing annuity, your payments increase with the constant rate. Present value goes down, and here is the formula how you can compute all these things. Well, you must be able to recognize these cases in practice, or if there is some suitable, let's say, practical case when you can apply one of these cases, do that. You must be able to understand when to calculate present value, when to calculate future value, if future value exists, let's say, if future value exists. Yeah. So, conclusion. In some cases, cash flows take a special form, giving us a chance to simplify the calculations. Annuity, perpetuity, growing perpetuity. You can either abstract from some specific situations and model your cash flow as one of these 4 types, or the practice itself tells that you need to apply one of these models, for example, in the case of a mortgage loan. So the next home assignment number 2, after the first part of this topic, is going to be available starting from today, I suppose. Let me check your page. Home assignment number 2. Yes, it is opened today, and it lasts 1 week till the next Saturday. There is still time to pass the first home assignment. Please make sure that you don't have any troubles with your connection and you are able to visit web pages. Yes, and one additional thing. So I hope that you understand the system, how we work with you. So today we discuss a new topic. Next week, exercise sessions, we solve some problems after this topic. So please, guys, those who really care about their studies and those who want to get a nice grade, read these slides before the exercise sessions, just to refresh your memory. I understand that after 1 week, everything is lost. I believe that after the lecture ends, everything is lost. So please keep reading, I post the video on the YouTube for your reference so you can watch it on the accelerated speed. Just make sure that you are ready to the exercise session next week to solve the problems. So the difficulty of problems is going to increase, and you must be able to understand what's going on there. Questions?
No question. Thank you, Professor.
Then it's all for today. Thanks for your participation. First group is free, and we meet with the second group in 30 minutes. Bye-bye.